Hello everyone. Today we're going to be talking about physics and how it's connected to global weather systems of the world. So we're not going to be talking about physics where it has a conventional connection to machinery or the mechanical world, but rather we're going to be focusing on weather systems and how physics can dictate these systems all around the world and how it affects our global weather. The natural world is full of physics and it's full of examples that we can see. Sir Isaac Newton himself developed his theory of gravity sitting in the natural world. Just like that. And with gravity, we're going to get into our first connection. Like I mentioned, we're going to first start talking about gravity and how the force of gravity and the concept of gravity dictates our global weather. So what I'd like to talk about is how changes in how distance from our Earth creates a stronger attraction of gravity on air molecules. Here on the lower fields, we sit at a lower elevation. This means that the air here is closer to the dense mass of our planet, and thus these particles of air have a greater attraction on the Earth and thus are much denser down here in the lower fields. As can be seen in this diagram, there is higher pressure at lower elevations represented by a denser variation of dots, and up here at higher elevations there is lower pressure. Here we are lower, and say we were close to a body of water like the Shad Creek. Warm, moist air here, because of collision theory, the air down here is much more dense and it is able to hold on to more water. Now, as this air, say there was a prevailing wind coming from this area and moving against the highlands of St. Andrews College, as this air ascends, it's going to have an interesting effect called relief. Okay, come. Obviously, the fact that I'm out of breath means that that was a high elevation to climb. It also means that as the moist water ascends this height into the less dense air on top of this cliff, what's going to happen is this air is less dense and it's much cooler because of this. This means that because of collision theory, there is less ability of the air in this area to hold water, meaning that relief is created. And what relief is as this moist water comes up and it's unable to hold the water anymore, the water condenses and begins to precipitate. This effect can be seen all around the world and has a huge impact on where we live as a species. As can be seen in the diagram here, as warm, moist air ascends this mountain, it interacts with the cold air at the top of the mountain, which, because of collision theory, the particles colliding less, there's less thermal energy up here, meaning that the air is colder. Once the warm, moist air reaches this lower density area at the top of the mountain, it condenses because of the cold and creates a zone of precipitation. The thing that dictates where winds are going to be traveling and how much moist air they're going to be carrying depends on A, whether they're coming off the ocean and bringing the warm airs evaporating off the ocean, as well as the direction of the wind. This direction is called prevailing winds, and it's dictated by the Coriolis effect. The Coriolis effect is an effect created by the spin of the Earth and other gravitational forces along with it. This effect dictates that air in the southern hemisphere will move from east to west, and air in the northern hemisphere the opposite, from west to east. Now we're going to be talking about a more pressing and current issue with our global weather systems. And this is, of course, climate change and what we can do with physics to help stop climate change. Our current world is highly industrialized and reliant on the processes of manufacturing with huge carbon emissions, as well as transportation through automobiles. These two facets make up over 50% of the global greenhouse gas emissions. A way that we can help to create new renewable energy that is good for the environment and doesn't create carbon emissions is through the harnessing of rivers like this. Maybe not rivers as small as the Shad Creek, but rather mighty water resources around the world. Through the construction of a dam, this water can be suspended ever higher into the air, creating greater pressure under its mounting gravitational force. Once this water is released in controlled amounts, it will have an enormous pressure, which will generate, of course, a massive force against a turbine, which, through electromagnetism, we know a great current can be created. We of course know that by looking at our induction equation, if we add a greater force to the armature of our motor, or rather the turbine, what we're going to do is we're going to create a greater change in magnetic field in our generator. This, by our induction equation, is going to create a greater delta phi, or a greater magnetic flux, and therefore a larger induction. Then from the simple running of water, we can create electricity for our power grid. But there's one other clean way we can generate energy. Another way that we can help address climate change and produce renewable energy is through nuclear energy. Though many people around the world are scared of nuclear energy because of its destructive potential when not managed correctly, nuclear energy only creates water as an emission product. This means that green energy can be created with barely any negative side effects. Obviously, the sun is out today, and it's quite powerful. Now, this is because of the inverse square law. The farther we are from the source, the sun, it follows a inverse of a square root in its intensity reaching the earth. This means that in the poles of the earth, during winter, because of the earth's axial tilt, they're much farther away from the sun. And because of the inverse square law, in those areas, they're going to experience less UV radiation and less light. This makes them cold in the winter and helps contribute to the changes in convection and changes in the currents of the air and water of our earth. Because of the uneven distribution of the sun's energy on the surface of the earth, areas like the equator have more thermal energy than the poles. This means that convection currents must be created to evenly distribute this energy throughout the earth. The concept of heat transfer is all proportional to the concept of energy trying to reach entropy. To reach entropy, energy transforms into many different mediums. In the video below, a pool ball makes contact with another, which transfers its kinetic energy into the pool ball, but also releases thermal energy as heat as well as sound energy. This energy transfer is the same for the convection currents of our ocean. Warm tropical waters are brought up north to areas with less energy, which evenly distributes into the land, creating the coastal climates that we on Earth love. Another factor which adds to the creation of a coastal climate is the difference in specific heat capacity measured in joules per kilogram degrees Celsius of water versus land. Since water has a higher specific heat capacity than land, this means that it can hold more energy per kilogram of mass, meaning that it can hold energy longer after a day and distribute it at night to the surrounding land as pictured in the diagram below. Today it is sunny and there's barely any wind in the air. But this could go completely sideways if a hurricane was to rip through Toronto and the Greater Toronto area. Nearly a decade ago, Hurricane Sandy came through and reached all the way to New York, bringing horrible effects primarily through its winds. Now these winds are all dependent on the direction, and that is what we're going to further discuss in a second. The real destructive properties of a hurricane don't come from the storm surge or the rain, but rather the wind and its direction. For a Category 5 hurricane, wind speeds need to exceed 250 kilometers per hour. What can make hurricane winds so deadly is the switch in the vector or direction of the winds. Since hurricane winds rotate in accordance to which hemisphere they lie in, according to the Coriolis effect, they have different directions of their wind. The northern hemisphere spinning counterclockwise, while the southern hemisphere spinning clockwise. Now, if the eye or the eye wall was to penetrate or go over a certain area, what would make the wind so deadly is the change in vector from one side going another way, and then the other side of the eye wall going the opposite way. There would be two separate winds in the same storm, which would make preparing for the storm impossible, making the changes in direction of the wind so deadly and hitting everything at every angle. When uninterrupted, sound traveling from myself reaches the microphone of this camera easily, but when behind this, it's obviously unable to pick up the sound as well. This is because there's an obstruction in the sound waves traveling through the air. A similar effect can be seen during a blizzard. Snow has many different crevices in it, which acts as an anechoic chamber. Sound waves in many different frequencies and amplitudes are able to be trapped within the minute details of a snowflake, meaning that sound is unable to effectively penetrate through a snowstorm. Those are just some of the ways that physics interacts with our natural world and ways that we can observe physics all around us on a daily basis. It's also some of the ways that we can harness physics to help us and help the natural world against some of humanity's most profound impacts on it. That's it, and that's all for today.